So this is the strain, this is the stress. The relation between the stress and strain matrix, and this one is material constitutive matrix. So this is the stress in two-dimensional case. The fourth step is derive the element stiffness matrix and load vectors. In this, if you want to derive this element stiffness matrix and load vectors, first of all, we have assumed the displacement function and the stiffness matrix or load vectors of the elements are to be derived by using either direct equilibrium method and variational approach or work energy methods. This has to choose suitable method to find out its stiffness matrix. In this, we will learn direct equilibrium method and variational method and work energy method one by one in the coming classes. So for understanding direct equilibrium methods, so we consider spring. A spring at node 1 and node 2, it has U1 and U2 are the displacements, F1 and F2 are the forces. So K superscript here is the stiffness of this particular spring. So 1 represents this one, spring 1. So under equilibrium, direct equilibrium conditions, we can say that this element stiffness matrix of this spring is Ke is equal to K minus K minus K, K. This is the stiffness matrix of this spring. So we may rewrite this one. Here is generalized K. Means suppose we consider this one is a spring 1. Because of the reason, keep it as K suffix 1 minus K suffix 1, K suffix 1 like that. We rearrange this stiffness matrix. How to find out this stiffness matrix, we will learn in the next coming classes. And assemble the equations to obtain the global equation. The individual element nodal equilibrium equations generated are assembled into global nodal equilibrium equations like K, Q is equal to F. Or for simple to understand, we may consider two springs. The springs 1 has stiffness K1 and spring 2 stiffness is K2. At nodal point node 1, U1 and U2, U3 are the displacements at node 1 and node 2, node 3, and F1, F2, F3 are the forces corresponding to this node 1, node 2, and node 3. So the node 1 element stiffness matrix K U is equal to F. So here K means stiffness matrix of this element 1. U means nodal displacements of this element 1. Force is F1 and F2 are the forces of particular node 1 and node 2 of this element 1. Similarly, at element 2 also same equations. It may change the only K2 because this is K2 is the stiffness of this element 2. So the KQ is equal to F. Simplified version, we may say that K2 and minus K2, minus K2, K2 and U2, U3 and forces F2, F3 corresponding this element 2 nodal points and force vectors. So these individual elements matrices are assembled into global position. So this one is node 1, node 2, node 3 represents this two springs nodal points. So it has 3 degrees of freedom. Totally it has 3 nodes, means in this case we will get the 3 by 3 matrix stiffness matrix and 3 column vector, nodal displacement vector, and 3 force vectors. So in this 3 by 3 matrix, stiffness matrix, global stiffness matrix will get. In this, first we'll substitute the first element stiffness matrix into global. So these places are node 1, and node 2. At the same time, this global place also node 1 and node 2. Corresponding, this one is zone 1, 2, 3, 1, 2, 3. So first we place the first element stiffness matrix into global. Similarly, we place the second element stiffness matrix into this global one. Here we are adding K1 plus K2 at node 2 because the element of first element second point and second element first point is placed at node 2. That's what we adding here, K1 plus K2. So similarly, the force also. The displacement is come U2. Though this one is finally we can modify it as K stiffness matrix, global stiffness matrix, U nodal displacement vector, and force vector. K Q is equal to F. Finally, we can simply say that K Q is equal to capital letters global stiffness matrix. And the next step is solution for unknown nodal displacements. So apply the boundary conditions to obtained global equations. K Q is equal to F means apply the boundary conditions of solving the set equations by two approaches. One is Gauss elimination approach, another one is penalty approach. And this Gauss elimination approach is very popular because easy to solve and finding the unknown nodal displacements in these steps. And third step is solve the element strains and stresses. In this step, we know the stress strain and strain displacement relations in the equation 2 and 3. And like strain is equal to dou by dou x, stress is equal to E into strain. So these equations already we know that. From these equations, we can directly substitute the unknown values of this strains, displacements, and substitute and find out the what is the strain of that particular element and stress of this element. So finally, interpret the results. Finally, to interpret and analyze the results for using the design and analysis purpose, determination of location in the structure where large deformations and large stresses occurred is general input or important in making design and analysis decision. So this diagram, deformed diagram, the variation of these colors is also represent the where the stress is maximum, is the minimum. Based on this, one design engineer can choose whether this analysis is suitable to continue the solution or not. If you want to solve this any problem by this finite element approach, must now follow these 8 steps or this procedure to solve this finite element method. Thank you.